I'll talk with somebody and they'll go, "Does this stuff really work?" And so I get my conspiratorial face on, and I can't do it right now, but I'll slide up to him. We'll get shoulder to shoulder, and I'll whisper in his ear, and I'll go, "No, it doesn't. But I've been able to fake it pretty good for 41 years now."
You're listening to the Foundry Talk podcast with your hosts, Nate McLain and Perry Merritt. Take it away, boys.
Welcome back to Foundry Talk. My name is Perry, and with me always is my partner, Nate. And today we have with us a fascinating guy, at least it's been fascinating the little time we've been talking before the recording, Dave Schmidt from Finite Solutions Incorporated. Dave works for a company, is actually VP there, that does analysis, flow analysis, solidification analysis, and I'm probably missing 29 other things you do, but of metal castings, and it's fascinating stuff. We're going to do things a little differently this time, and if you have the ability to actually watch your screen as opposed to just listen, you may want to take advantage of some of the things we're going to show you today. Dave is going to show some of the solidification and flow and just things that go on in the simulation. And it's actually fascinating stuff. So I'd encourage you to watch if you can. If you can't, there may be some other options, and I'll let Dave talk about that in a minute. So Dave, welcome. It's good to see you. And I thought we would just kick it off a little bit. Tell us a little bit about FSI.
Well, Finite Solutions was officially formed in the early 1990s. But I would say technically we've been around since 1985. At that time, I was working for the American Foundry Men's Society, which is now the American Foundry Society. That shows you how long ago it was. And I ran what was called the AF Software Service. It was the computer software branch for microcomputers. Originally, it was for the Apple II computer, and then quickly that turned to the IBM PC. But basically, PC-based solutions. We originally started out with worksheet-type programs, not specifically spreadsheets, but calculating riser sizes, calculating furnace charges, things of that nature. But in 1985, Larry Smiley, who is now the president of Finite Solutions, came to me. He wanted to write an article for Modern Casting magazine on a tool he had developed to help predict solidification in cast parts. And it was ultimately the world's first commercial PC-based simulation model. Just a little bit before that, he was working at Reliable Castings in Cincinnati. His father-in-law owned the company, and he kind of married into the business. And he went to a seminar at the University of Wisconsin to learn more about solidification. And I didn't meet him at that time, although I was involved with that program. It was called the Cast Metals Research Program. And he wrote a PC-based solidification model. Now, at that time, computers weren't very powerful, so it was a 2D program. That is, you created a slice from a casting, and you watched it solidify from the edges in, if you will. Very simple, but also very informative. And he just wanted to tell people that you could write programs like this to help yourself. And when I saw that, I encouraged him in that, and I said, would you be interested in making this available to other people in the industry? Because, of course, he's working at a foundry at the time. And he said, well, I would, but I don't have time to do that because I'm an operating foundryman. And I said, well, I spend my full time selling computer programs to foundries. So at that point, AF Solid was born, and it was, if you will, the flagship product of the American Foundry Society. And it was 2D in the 80s, and into the early 90s. In 1992, it became a 3D program as computers became more powerful and we could expand capabilities. And then in 1995, I joined him so that we could focus 100% of the time on simulation as opposed to some of the other things that I was doing at AFS. And as I say, the rest is history. We went from DOS to Windows to 8-bit, 16-bit, 32-bit, now 64-bit. And ironically, there is more development work to be done now than there was with the first simulation tool we published. And the reason for that is the technology has improved so much that you can do stuff that we couldn't even think of doing in the past. For instance, fluid flow analysis. You could run that on a mainframe computer if you had a couple of weeks of computation time available to do one iteration. Now, a lot of our, I'll call them routine jobs, full fluid flow analysis and simulation can be done in minutes with quite complex models. So just the technology improvements have made so much more possible.
Yeah.
That's what we do. That's in a way all we do. We do simulations for people. We do contract work to fix problems. But most of our work, of course, is in demonstrating the product and doing technical support for existing users.
So, for foundries, David, what are that aren't currently using simulation yet? What do you think that some of the biggest misconceptions that you hear about simulation in general that you hear out in the world, trade shows or whatever, that people think that they understand or that stuff doesn't work type mentality?
Well, interesting that you should use that phrase because one of the
Well,
things
usually
that,
it's a lot harsher than that.
well, quite often
There's usually a 4-letter word thrown in
Yeah.
there.
I'll talk with somebody and they'll go, "Does this stuff really work?" And so I get my conspiratorial face on, and I can't do it right now, but I'll slide up to him. We'll get shoulder to shoulder, and I'll whisper in his ear, and I'll go, "No, it doesn't. But I've been able to fake it pretty good for 41 years now." And I mean, I understand where they're coming from, but by the same token, if it truly didn't work, none of us would be around anymore. Now, that's not to say it's perfect. It isn't, and it never will be. It will continue to get better and better and better. But it's a tool. It always has been a tool, and it always will be a tool. But it's becoming more and more sophisticated and more functional in what it can take into account. And so it allows somebody to look in the mold. And I think that's probably the most important feature of simulation. It allows you to literally see what's happening as opposed to inferring after the fact what must have happened in order for this to occur.
Sure.
So, for example, in a fluid flow analysis, you can see a wave of metal go down a runner. And if it's not filling the runner, what happens? You get a wave. And when it hits the end of the runner, you get the tsunami coming backwards. And oh, look at that. You see that hole in the middle? That's air. That's gas. That is now getting mixed up in your metal, and it's turning your good metal into crap. So, the things that you've only guessed at, you literally have a much better handle on, and you can use that to improve your processes.
Sure.
You talk about that. I'm flashing back to, there was a guy on YouTube several years ago now, probably 4 or 5 years ago, that was he was making molds in sand, and then he was, for example, he would do it vertically, but his runners and stuff would go across the front. And then he put a sheet of glass against that sand so you could see it. He would pour in there, and that metal coming down across the runner and hitting the back wall and folding back over itself and doing
Yep.
clearly visible in the mold. His was a little bit exciting. His was more exciting than simulation, and that his glass would explode shortly after filling. But you know, it was fascinating to see what was going on inside the mold. And and once you showed us earlier today, I'm hoping we'll be able to look at the flow analysis. It's fascinating stuff to me to see how that metal goes into there, enters in, and so
Yeah.
As I said, I've been doing it in one form or another since 1985. So I am more than 40 years into it. And you see some, as you say, amazing things for a lot of different reasons. But I can think back to one investment casting that was the geometry of the part was not complex. It was pretty much a plate that had a fairly sharp edge on one end, and it had some holes in it, but it was cast in the most complex system I had ever seen, in that it had a primary runner and a secondary runner, and the metal took a bypass because there was a ceramic plug in the shell. The metal went across that, went down the secondary runner, down to the base of the casting, came up through a filter into the primary runner, and there were several gates on that. And then as that runner filled up, the metal would squirt into the casting across these cored holes. And so all the work that you had done at the bypass and filter was completely obliterated by the fact that you sprayed the metal in after you had done it. And their intention had been to do this so that they could get quiet filling.
Yeah.
But by not being able to see it, they really didn't understand what was actually going on in the
so
process.
their quiet filling became a jetted filling where metal's just jetting into the mold
Yep.
cavity.
Same sort of thing we see quite often, primarily in larger steel castings, where bottom gating is very prevalent. Multiple ton castings, they'll have ceramic tile gating systems, basically pipes where the metal is coming through. And it'll go underneath, and then the gates will come up under the casting and they'll be vertical. Well, guess what? You've created multiple fountains of metal, and you can see in a filling analysis, you can see literally, you go to the park in your town and you see the fountain.
Yeah.
Metal
Not good.
behaves the same way when it's liquid. That's exactly what it looks like, and it takes about 70% of the casting to be full before that calms down.
Oh,
Yeah. But really bad engineering.
But
Yeah.
again, you think, oh, I'm going to put it in the bottom. That's going to be quiet. Well, if you brought it in horizontally, that would be one thing. But by changing it to a vertical, you're creating a spray. But again, you can't see that in the foundry. You have to have another way of looking at it, and that's what simulation can do.
Yeah. So I'm sure I mean, at what point did you realize, which you've been doing it for a long, long, long time, 40 years, that simulation was, it was no longer really, just nice to have. It was, but it's become, for modern metal casters, almost essential.
It's when people came to me for simulations because the customers were requiring that they have evidence
Okay.
of it.
evidence of what? Of how it's filling, or just how it's shrinking or cooling?
The customer were requiring the foundry to show evidence that their system, the system they were designing was going to work, and that needed to be done through simulation. And I had one really interesting thing. Well, actually, it was with Larry while he was still working in the foundry. They had one customer who over the years, it had been I guess you'd say, a fairly tense relationship. They would talk about making adjustments to the process or some design changes, and the uh, the end user was never easy with that. And once Larry had written simulation, that they had one part that they had gone through and they had tried rigging it in various ways, and the crux of the problem was the design of the part, as happens a lot of time in the foundry. But
Absolutely.
they talked about making a design change, but this time they had simulation results to not only show that there was a difficulty, but to show that by making the design change, they'd be able to successfully cast the part. And so they come in ready for the big fight. They've got all the adrenaline going, and they laid the sheets out and showed that. And the guys looked at it and go, yeah, okay. And they immediately signed off on the design change. They left that room wanting to knock holes in the wall. They had all that testosterone and adrenaline built up for a fight that they never got. And they couldn't understand it because this was a customer with a history of that sort of thing. But then they sat back and thought about it. It was the first time that they had shown the customer evidence that what making those changes was going to do. Think of it from the customer's perspective. You send them a drawing, you ask for a quote, you assume they're going to sit down and figure out how to make it before they create that quote. Okay, they do that, you accept it. They go and make something and they make scrap. Then they try some other things, and then they come back to you and say, oh, well, the problem really is that your design is flawed. But if you make this change, it'll work. Are you going to believe
Right.
that guy? That's what he told you the first time, and it didn't work. And now it's my fault, but if you make the change, it'll work. So when you think from that point of view, it totally made sense the way they had behaved in the past. But now it also made total sense because they had objective evidence that showed that it was going to work. And so that seal of approval, if you will, has become much more important since simulation has been around for a significant period of time, and it has proved that it can be very useful. But again, it's still a tool, so you're not getting it 100% of the way, and even very good tools can be used incorrectly.
Sure. Yeah.
And
Case in point, I mean, we've had the situation where um, doing pump parts and things of that nature, whether they're copper-based alloys or stainless, duplex, super duplex, what we run into is sometimes the simulation that looks, it looks like you've engineered it properly. You got no shrink. You've got your turbulence. You're staying below 20 inches a second for your fill rate. All those sort of things. You're doing the right things. You're not using conical pouring basins. You're pouring. You're trying to stick to Professor Campbell's 10 rules. Good melt quality. All those sort of things. And that's always being refined all the time. None of us bat 100. But with that being said, sometimes you'll have an anomaly and you'll get a shrink in an area that you didn't anticipate. It's like, hey, this doesn't match what happened with the simulation. But then you go back and you watch the video of the pour. You pull the information of what the ladle temperatures were, what was the pour time, all this sort of thing, that the actual information. And then you go back and you feed that information back into the simulation software, and guess what? The defect that we're seeing in the real casting is right there on the screen, because something wasn't simulated. Because technically that's theoretical, right? It's in a lab setting, but in the foundry, something may have changed. Something was a little different. And then when you go back and you look to make sure that the gating is actually what was simulated and all those sort of things, then the defect shows up, and you're like, it's right there in front of us. It wasn't apples for apples. So then you correct it. Next time you pour it, guess what? it's gone. Everything's fine. So it does work in that regard. If garbage in, garbage out. So
There's actually a couple of aspects to that situation. Um, the first thing is you talk about the garbage in, garbage out. You want to have reasonable data of your process. So uh, here's a silly example. We had a company that had been using our software for quite a while, and they were having difficulty with the part, and they very often what we'll do is we'll say, okay, well, export the model out of the system, send it to me, and we'll take a look at it. And the first thing we do is we go through and we look at uh, the conditions, if you will, and we make sure that is the property data reasonable, that. And this guy was using a filling temperature of, or excuse me, a filling time of 30 seconds. And I was going through it and I'm looking at that and I look at, the gating system isn't filling up. And I went back and I said, well, one of the things I noticed is it seems you're doing a very, very slow pour. And he goes, no, we're not. And I go, excuse me? He said, no, it fills in about 5 seconds. And I'm going, well, your simulation is doing, you can change the filling time?
ah,
You know, and it was, yes, you can. And so is that a fault of the tool?
no.
There are things like
Operator
that.
error.
But then there's also, are we modeling what's really happening? And I guess that's sort of the way it is, but like you talked about, well, it turns out that we had a problem, getting metal into the ladle, so it was hanging around for 15 minutes before we poured it up. And so your pouring temperature was what compared to what you were doing a simulation?
Exactly.
A given simulation uses a set of conditions. And if you run that simulation again using the same conditions, you'll get the same result. Whereas in the real world, we do things under a range of conditions. So quite often, especially if you know it's going to be a sensitive part, it makes sense to run simulations under the range of conditions that you might expect to reasonably see out on the shop floor and see, is our process robust enough to handle those?
Those worst
Obviously
case scenarios.
there are going to be crisis sorts of things, that are going to mess up anything. Uh, we didn't get the cope in place, and all of a sudden things are sliding. Okay, well, simulation's not going to help you with that. But finding out how much variables mean to the process is another aspect of using simulation that can be very beneficial. You can even do, to a certain extent, designed experiments using simulation where you can more or less automate the process and say, oh, okay, I know that my pouring temperature is going to vary by up to, and I'm just picking a number, 150 degrees. Okay, if that's the case, I can set things up and have the tool run 15 simulations, automatically changing the pouring temperature by 10 degrees each time. And you're only setting up one simulation, but then you can find out, okay, how important is it to maintain a tighter range?
But I'm going to ask a dumb
That's
question here
intriguing.
because I don't have the software. Is this software, is this simulation package something that the Foundry actually purchases, subscribes to, or something and they run their own simulations, or is this something that FSI runs for the customer?
The answer to that is yes.
All of the above, then, huh?
Exactly. A normal sequence for us is to, especially nowadays, and what I mean by that is since simulation has been available for a pretty long period of time, uh, most of the people that come to us are either new to the industry or they're having a problem and they're not using simulation. So quite often our first contact will be contract simulation for the express purpose of fixing a problem. We strongly believe that people should be using this every day on everything they do. We've seen too many situations where they wait until they get into a problem, and then the cost involved to fix that problem would have more than paid for having the tool available to them anytime. But that's a typical starting place. But after doing a couple of jobs and proving that this technology works, it is by far better, in our opinion, for the foundry to do it themselves. And there's a number of reasons for that. Number one is simply the time factor. You have the model. If you can work on that right away, you're going to get your answer significantly faster than I can get it to you. Number two, you can take into account many variations very quickly, whereas we look at one result and they say, oh, can you try this? Can you try that? Yes, we can. But again, every time you do that, there's an additional time lag in that. But probably the most important reason is the guy who's responsible for making that casting is the one who knows his processes. I know the software, but I don't know your processes. So making decisions and choices on things, I could do things that would be completely out of touch for your business, even though from a mechanical standpoint, that may be useful, but it may not be appropriate for what you're doing. And so those sorts of things. The other thing is we're a small company, so our time and resources are best spent in improving the product so that the 800 plus companies and schools that use our software can all benefit from that.
Yeah, and I can see even if your intentions are pure, right, that you could still miss things because Nate forgot to tell you that,
Sure.
oh, while they're ladling the software, the guys who went off and having a break and then coming back. And, you know, there's just information you're not going to have that the guy who's making the casting has and just knows intuitively when he's setting up the software. So,
Oh, well, a perfect example. This is many years ago, but I guess it really doesn't matter. But we were working with an investment foundry that didn't have software, and they were really interested in rapid prototyping, and getting wax patterns made via rapid prototyping so that they could immediately dip them and pour the casting. Well, they were working with a setup where I think they had 3 free samples, if you will, and they had rigged 2 of them and had come up with really bad castings. They weren't getting the result they needed. So they were down to one last chance. And so they said, oh, well, maybe we ought to do some simulation to see if we can get this. And we agreed to do it. And we said, okay, your process, took all those things down, and we ran simulation. And they go, oh, no, that's not at all what we saw. And as is typical in a situation like that, where simulation results aren't matching shop floor, we go through this step-by-step process. We start with, okay, let's look at the material properties. Let's look at this, let's look at that. And everything seemed, from what they were telling us, right in line. So we were kind of stumped from our end. And I said, okay, is there anything else you can think of that you're doing in this process that we haven't talked about yet? And we were talking with two guys from the foundry, and one of them was kind of scratching his head and going, and then he goes, well, we didn't talk about canning. And I go, okay, canning, what's that? You'll have to explain to me a little bit more. I said, well, this is a highly oxidizing alloy. And so what we do, as soon as we pour the shell off, we throw a big pile of sawdust on it and we cover it with a can, and the sawdust
Kill the
ignites,
oxygen.
gets rid of the oxygen. Okay. So you're adding fuel, you're containing it, and you're heating up the thing. Do you think that might affect the heat transfer of the process? Well, Larry and I were not investment casters. We had never heard of that. And so we had nothing in the software that would take that. But Larry was famous for this, especially in the early days. The next morning, he said, I think I've got the radiation view factor stuff working out right. And he had come up with a way to simulate canning. And so he ran another simulation and he looked at it. And they said, that's exactly what's happening. So now we had 100% confidence of going through and adjusting the rigging to make a good part. We were able to do that. And the third prototype showed that that worked. Well, they've been using SOLIDCast now for over 20 years. And it was because of going through that process that obviously gave them the confidence that they needed to do that.
So did they still can that job by chance?
I can still remember that they had like a spiral gating system around the outside, and CAD tools were not as sophisticated back at that point in time. So it just creating the thing was a kind of a
Nightmare.
stretch.
Yeah.
I always
Interesting.
used to joke, again, in the early days, when we first came out with 3D simulation, the problem is that Pro Engineer was the only 3D CAD system, and it ran on a Silicon Graphics workstation. So to realistically create good models for running simulation, you had to have a CAD tool and an engineering workstation so that you could drop things down to your PC. Well, that's now available for, quote, everybody everywhere. So that's really another reason why this sort of stuff is much more usable now, because the auxiliary pieces are there where they really weren't when this was just starting.
Sense. Yeah, I mean, solid modeling software. I mean, you can get it dirt cheap. Anybody and a hobbyist can have it at home. So it's grown exponentially. It's amazing.
My 9-year-old grandson has a 3D printer.
Yeah. Yeah.
He makes toys by
Yeah.
designing them in CAD and then printing them out.
Yeah. Pretty amazing. Pretty cool. Yeah. I mean, it's not the Jetsons, but it's getting there. It's pretty cool. We're not flying in cars yet.
He also plows the family's driveway in his pedal car.
Oh, nice.
His dad built a snowplow blade for the front of his car, and this kid literally plows the driveway.
That is awesome. I'd love to see a video of that. That's cool. Well,
When it
that
warms
is
up and the snow gets
slushy.
nicer.
Yeah. Yeah, for sure.
All
For
right.
sure. So I mean, so that is a great example of how a simulation has saved a foundry. You know, a lot of work and an expense for a mistake and that sort of thing. Um, do you see that foundries that I mean that they some project that they've lost? They've been losing a lot of money, or they're going to lose a project or lose a contract completely. And so they just have to come to. I mean, they're just like, hey, we're in a panic. We got to get this done, type thing. Does that still exist, or do you see that the people have in metal casting have kind of made the turns like, okay, yeah, no, this we have to have this? Or are there some foundries that shouldn't use simulation yet, or maybe there's not any?
From my point of view,
Well,
um,
sure.
you just gain knowledge. I mean, it helps you do your craft. And let's face it, metal casting is a craft, but there's a lot of science to it as well. And there are ways that you can apply that science to it in a much more consistent way. So I truly feel that everybody can benefit from it. But oh yeah, it's probably not as frequent now as it may have been years and years ago, but we've got jobs all the time that, yeah, I'm in a real problem. I had an example of a guy was doing a ductile iron camshaft, and they had been working on things, and they were having all kinds of difficulties with it. So they were coming to us for contract simulation in order to fix a problem. And the way in which we typically work is we run simulations to predict the known defect. And then more often than not, we rip that all off and start from scratch. But that gives people the confidence of knowing that, well, this was ductile iron and they had a match plate pattern, and there were two camshaft castings on the pattern, and they were splayed out at an angle. Okay, so they weren't parallel, they were at an angle to each other. And there was a riser at one end, there was a riser at the other end, and there was a huge central riser that fed both of them in the middle. So 5 risers to feed 2 castings. And they were getting shrink problems all over the place. Well, I was asking them for the gated setup, and they didn't have a model of that available right away. So I said, well, get me the dimensions and we'll create it. But in the meantime, they sent me just the camshaft. And I ran the camshaft, and as we in cast irons, we have this dichotomy where the iron shrinks initially, but at some point, depending on the chemistry and the cooling rates, etc., you'll get graphite expansion coming out, and the casting will stop shrinking, but will actually become self-feeding. And there are a couple of rules that go along with this. And one of them is if you find a feeding zone, and I realize I haven't defined all that, but if there's one feeding zone in the casting, then you can only use one riser. If you use more than one riser, you will actually create a shrinkage condition, not alleviate it. Whereas in shrinking alloys like steel and aluminum, if you get a casting that's too long, typically we say, oh, well, we've exceeded the feeding distance. So we put another riser on, and that helps feed the shrinkage there. Now, that reduces the yield, but generally, even if it doesn't completely fix the situation, it doesn't make the situation worse. Whereas in cast iron, you will make it worse. Well, I ran this unrigged simulation on the part and found that it had one feeding zone. So this was literally while I'm talking with them on the phone. And I said, okay, I don't have the solution for you yet because we haven't gone through the rigging, but I do know what your problem is. Your problem is that you've got 4 too many risers on this pattern plate. What you should do is you should move the impressions so that they're parallel and do one central riser between them, and that will take care of it. And it goes, you just solved what we've been trying for 6 man-months to fix. So there were two guys that had been working on this problem for 3 months apiece. And I was able to come up with the solution through simulation in 10 minutes or less.
Mm.
Now, why did that happen? It happened primarily because they didn't understand some fundamentals about the way cast iron solidifies. So is that the fault or the reason for software? You could argue both ways on that. But what it does say is that by doing simulation, you can very quickly get a true understanding of what's going on, and you can come up with an appropriate solution. I probably go to cast iron more often than any other material because those anomalies can be pretty spectacular. We've got a great example. It was from a foundry, happened to be in Australia. It was a big cover casting for hydroelectric power. I don't even remember the diameter. It was like 6 or 8 feet in diameter. So a really big ring casting, multiple tons. And we got the job on it. They said it was the 7th iteration in the foundry, which implies that there were already 6 failures. This casting had 36 top risers, all with exothermic sleeves on it. So you not only have a huge number of risers, so there's a lot of effort in that, setting all the sleeves, the cost of the sleeves, a very expensive process. And it was just riddled with shrinkage. So we take the casting geometry, run our unrigged simulation. We determine, again, within about 15 minutes, that the ring is actually a single feeding zone, which says it needs 1 riser, not 36. Well, the toughest part about that was actually getting the foundry to accept that and to run it, because they're saying there's no way. But again, it was a fundamental misunderstanding of what was going on. Well, we got them to do that, found out, made a perfectly sound casting, improved the yield by, I don't even know what percent. I mean, saved several thousand pounds of metal per casting in that, plus all the cost of the sleeves, everything else, with about 15 minutes of simulation work. So there's some that aren't nearly that spectacular, but there's a lot that are. We haven't even discussed the idea of optimization, but everybody's got more jobs to do than they have time to do them. So
Sure.
the typical foundry engineer, whatever method he's using to rig castings, whether that's by experience, whether it's worksheets, whether it's simulation, you get to a point where you got something that works. That's typically the end point.
Yeah.
But if you've got a part that you're going to be making over and over and over again, wouldn't it be nice if we could do that in the most efficient way possible? We've got
Sure.
a given layout and we see it makes a good casting. Well, are there other layouts that could be done that would make a good casting, but do it more efficiently? Pour less metal, higher yield. Well, optimization can be done where you can set up what can vary in the process, how you say it's good or bad, and typically that's shrinkage related. And then it can be set up to run automatically. And we typically see yield improvements from anywhere from 5 to 15% using setups like that. I said, well, over the lifetime of that part, do you think a 15% improvement in yield is going to make it more profitable?
Yeah.
Sure.
Well, that could be the survival of a foundry.
Absolutely.
And
Yeah, for sure.
ironically, that's something that people don't use very often, even though it's been available for almost 25 years.
And that's the OptiCast portion of the software.
Yeah.
Okay. And so OptiCast, is it more of an automated process once you have
Well,
solidification and,
you
and
do an
flow?
initial setup, but that's the whole idea, is that all of this gets done without operator involvement. For instance, let's say you've got a multiple riser situation, and it's not a symmetrical case, so they're all kind of independent from each other. So you could say, okay, I want the height and diameter of each of these risers to vary. And that could involve getting taller or wider as opposed to smaller. It all depends on the dynamics of what's going on there. And we had one example where we had 5 risers. We did the height and diameter, varied on them. It took 100 simulation runs to do that. But after the initial setup, which was basically clicking on each riser and saying, okay, what ranges could it go through? And then saying go. The next morning in that case, it was all right. 100 simulation runs later, we now have a 12% increase in yield. And in that particular situation, it actually solved a shrinkage problem as well. Because there was one riser that not only was it too big, but because of that, it was overheating a part of the casting, and it was changing the directionality of solidification, and it was creating a hot spot that wasn't being fed. And by reducing that riser size, it actually improved the solidification behavior as well as improving the yield.
Fascinating.
That was a very useful byproduct in that case. That doesn't always happen, but it can, and I've seen it happen more than once. Another interesting sort of variation on that is you can actually have a riser size go to 0. In other words, if a part is over risered and that riser isn't necessary, eventually it will disappear from the model because it doesn't have a beneficial effect. And we've seen that happen as well.
And that's all that's all done automatic in the software itself.
Yeah.
It just runs those iterations until it finally deems itself, hey, this is the most optimal yield.
The technique is called response surface methodology, and I'm not a mathematician, so I'm not going to go into it all. But the idea is, think of like you're trying to climb a mountain, and the mountain has little bumps and gullies and things on it. It's not just a smooth surface. You don't just go straight to the top. What response surface methodology does is it gets you to the top, or as high as you can go. It might not be a point, it might be a mesa or something like that, but it gets you from the realm of, okay, any number of things could get you, let's say, a shrink-free casting, but which one would have the highest yield? And it's a way of turning that from an infinite number of points to a finite number of points, which can be evaluated then and then compared. So yeah, once you do the setup, it's 100% automatic from that standpoint, or from that point on.
I'm going to make a little bit of
Okay.
a
No,
suggestion
that's
here,
outstanding.
because we've been talking for almost 50 minutes, and I feel like we could talk for another 2 hours, and we still haven't shown a simulation. So I'm going to suggest maybe we take a quick break. Dave, you get the simulation set up, and I'd like to kind of just show that and be able to kind of walk through what sort of things are available.
This is very typical of a casting geometry. It's a ductile iron base. One thing I wanted to show here is that this is actually made up of a bunch of pieces. There's the main geometry of the part, but there's also a number of things like we've added in machining stock in other things. So you can have simple parts, you can have very complex parts. If we look at the materials, I'm going to click on, this is the data for the ductile iron we're working with. And we look at 2 things simultaneously. We look at temperature, or the solidification aspect, and we also look at volumetric, or the shrinkage aspect. And in the case of cast irons, they're unique from the standpoint that they start by shrinking, and that's this blue line going down to the right. But at some point, depending on their chemistry and the cooling rates and other things involved, the graphite is coming out of solution in the iron and it's creating an expansion situation. So, number one, the amount of metal required to compensate for shrinkage is less in an iron than, say, in a steel or an aluminum. But also the way in which it occurs is different. So we need to take that into account in our simulation. And the way in which we do that is we start with an unrigged simulation. And I'm going to create a mesh here, which is just a series of cubes. And that's what the simulation is actually run on. And this shows visually the casting geometry being built up.
And what size are the cubes, David, that are
In
filling
this
that
case,
area?
they were an eighth of an inch.
Okay.
So, in fact, since you mention it, let me just go into the view and go
Is there
into
is there a minimum? Is there kind of a sweet spot just to for efficiency for time and still get good solidification data on the size of the squares?
Typically you want your cubes or your nodes, as we call them, you want a minimum of 3 nodes across any surface that you're going to be working with. So like through this flange here at the end. This particular model I was watching as it meshed, it's about 1.6 million. We can do as many as 120 million. You don't want to do that unless you have to, unless you have a very large but thin-walled complex part, because of course there's a lot of calculation involved with that. But just as an idea, I'm looking at this part 7.7. So this is about 15 inches across, left to right here, just to give you an idea. Okay, so we go to run our simulation, and when we say yes, we'll see the system run, and this is just a mock-up of the casting, and you can see the temperatures change. As an area solidifies, it goes clear, but you can adjust how that looks. You can change the angles you're looking at. But this is basically just to let you know things are running. Over on the right side, it tells us the process, the simulated time, temperatures in the casting and the mold, number of time steps. We're at about 2,700 right now. And each time step, we're doing 1,657,350 sets of temperature calculations. So there is a lot of stuff going on here. Now, notice that we can see that areas have separated in the visual view. We've got an isolated spot here on the left, and in a moment, we'll have 2 other areas on the right and the upper sides. So we have 3 different areas that appear to isolate. And if this were a shrinking alloy, that would be an obvious indication that we would need a riser to feed each one. In other words, we would have to bring metal in on the lower left, on the upper right, and on the top in order to feed this casting.
And this is a simulation of gray iron or ductile iron, David?
This happens to be ductile.
Okay. So it's finishing up currently, just for those that are listening and not watching. So
Okay, so we've finished that simulation, and it's now loading the results. And we have a riser design function that allows us to predict the number of feeding areas or feeding zones. Now you can see that it lists 2 of them here. And if we want to see what those look like, we can see one here, and then obviously because there's 2, the other one would be the other side. Now, because this is a cast iron, we need to go through and test those. In other words, at the time when expansion starts kicking in, are these actually still connected, or do we truly have isolated areas? And there's other functions in the wizard that do that. And we don't have a lot of time here, so I'm going to jump forward to the results of the riser design and the gating design functions. So I'm going to finish this off, and now I'm going to choose there we go. This is going to be a rigged model. And we could see that it has a pouring cup, a down sprue, a full gating system, including a ceramic filter. It has risers, and it has gates. Well, all of those components have been calculated by the software based on the results of that unrigged simulation.
We're looking at 2 parts here, right?
In this case, we've decided that we wanted to put 2 parts on the pattern to improve our yield. So we have 1 riser on each part instead of the 2 that we would think we would need, because our feeding zone analysis told us that those were connected at the time where expansion begins. And again, I've skipped a few steps in the process, but all the dimensions of this, and in fact, the filter itself, and in many cases, the risers, can be created within the model building tools within SOLIDCast itself or in any CAD system. Now, I have run this simulation, but the fluid flow analysis and solidification took about 45 minutes to run total. So when you add size and complexity and more analysis, it does take longer than the 2 minutes or whatever it was to do the unrigged simulation. But let's go take a look at what we can see from the fluid flow. First of all, the system calculates an appropriate pouring time for us, and we can either accept that or we can adjust it. But once we've moved forward on that in the gating design, it helps us design the appropriate sprue, runner, and gate sizes to meet that pouring time. Now, if I go to the animation tab, I can replay this.
So we're watching the mold cavity fill,
Right.
giving the temperature gradient.
And in this case, we're looking at temperature. We can go, I have smaller pieces here because I saved them in bigger chunks, but we can also look at things like metal velocity.
So Dave,
And you would...
can I put
Yes.
you on the spot here, Dave, and ask you to look at something? Maybe you'll tell me no.
We'll see.
But that gate, that perpendicular gate, the gate that's perpendicular to the rudder, kind of in the middle there, can you isolate when the metal initially flows past that gate and see what happens there?
Yes, there's a number of things that you can do. We can do what's called flow path lines. And so this shows the path that the initial metal took. This shows metal that went into the sprue 10% of the way through, 20%, and we can change colors and size and things like that. So we can do that. That's one potential. We can look at what we call fill temperature, and we can look at fill time. So if we plot fill time, let me turn off the path lines. Okay, this shows the relative time through the 22 seconds of when the metal first hit a given area. So for example, if we look at this gate over here where it connects to the casting, that took about 3 seconds to fill to that point. Whereas the top of this riser didn't fill till just over 20 seconds. So there's a lot of different things you can look at. You can look at the temperature at which the different areas first filled at. You can look at metal velocity. You can look at pressure. And of course, this is a sand mold, and we're basically with atmospheric pressure. So the pressure shown here is based on the head pressure as well as the pressure within the filling process. So there's lots of different things that you can look at. The majority of people, I would say, look at temperature. You can also put in what we call velocity vectors. So you can slice an area and see were things swirling at a given time. If we had had a bigger gating system, you can see it more often in investment castings where you have a chunkier, a blockier gating system. You could see the metal flow down the runner and then backfill or splash back. So if we went to the animation tab, I'm sorry, I need to go back to our status tab. So in this case, I can see what's happening at 20%. I can see what's happening at 40%. So you can look at any point in time and see what's happening. For instance, we can see metal here on the left is sort of splashing out and falling. We can see that the runner extension here, that's where the first metal that came down the runner is sort of trapped, and we can see that that's cooling off. And the idea of that is that it will hold any impurities that were in that initial metal or any sand particles that may have been in the mold initially and keep them from flowing into the casting. So there's a lot of things that you can see from the filling process. But in addition to that, it's setting up the solidification process in a better way because it's accurately depicting the temperature changes during filling. Now, in looking at the simulation results, I'm going to go into a slightly different results viewer here. And I'm going to zoom up a little bit. And we can do what we call a cut plane plot, where we can cut and print, if you will, on a two-dimensional plane. We can also do what we call the cast pick, which will do a 3D of things, and we can rotate that around and move it. So this is showing a progression of solidification, and then we can go to what we call the material density factor. And I'm going to go back to what we call an isosurface. Oh. And I'm going to plot at a level of 0.99. And so what we see here is kind of an X-ray view where we're looking through the parts and the gating and we're predicting shrinkage. A material density factor of 0.99 means if a given area has lost than 1% of its density during the process, it will be plotted here. So we can see the initial drop of metal in the pouring cup. We can see the drop of metal in the risers. We can see a little bit in the base of the sprue just below or above the filter chamber, but we can see that the casting is completely cleared. In other words, we've created a sound casting using this gating design.
Okay.
Fascinating.
So it's very fascinating. It works extremely well. The and really the design itself, this design, it was done with OptiCast portion of it, or was this done by
This
an
was not
engineer?
done with optimization. In I would say, quite honestly, optimization can be used with cast irons, but it is probably less useful because we did the riser design and the contact design specifically to have things shut off at an appropriate time. Whereas if this were a steel casting or aluminum, you could probably apply optimization to it more readily, or you would have a better potential for an improved result, I would say. I've done some things with cast irons, and for example, I've optimized the contact and found out that it was 1% different than what the initial calculation came up to.
Okay.
But we have a number of examples. Let me see if I can find it here. Hold on just a moment. Clear off this part. Looking for piling hammer. Case study. Okay. This is the unrigged part. I'm sorry I didn't have the rigged one here, but basically we went through gating and riser design and came up with a single top riser for this piece with a bottom gating system, and then did an optimization on it, and I think it was we were able to get a 7% yield improvement from what was initially calculated by using optimization. And that probably took, I think it was 12 simulations to get to that point. But again, those were all done automatically after the initial setup. Yeah.
Cool.
So you can apply it to anything, but it's probably more applicable to shrinking alloys than a cast iron, because there's more features within the design for cast irons that need to be specifically controlled. And once you're doing that, you're really getting the most out of it that you can.
Okay.
Great.
No, that's
You
outstanding. No, so a lot of the
no,
go ahead, Perry.
Go ahead. Go ahead.
Well, I was going to ask, so a lot of the examples were, just to be in full transparency, anybody that's listened to the podcast knows we're huge John Campbell fans. Professor Campbell has been amazing whenever it comes to to just moving the ball forward with metal casting and reducing oxidation and defects and really trying to fill the mold in a manner that doesn't exceed um, the terminal velocity for the most part. I mean, so that we're not sending the metal in there, squirting it in there, and we're introducing a lot of air, as we've talked about as well. I know you were mentioning doing everything you can, especially when it's aluminum and steel alloys and that sort of thing, to eliminate the mixing of air and metal to make it more a more refined pour. I was just curious, do you see very many people doing that? Because most of the time, what we see are um, round tapered sprues rather than square or rectangle sprues. We see the use of splash wells still today, rather than a transition from vertical to horizontal using a radius, nice transition, that sort of thing. Some of the things that are talked about in Professor Campbell's mini casting handbook. Hold on a second. I don't know if you've seen this one before, David, or not, but I'm just curious if do you see that much of different designs like that? Because traditionally, what we typically see, the AFS gating systems are heavily used, but it is not seems it is a source for many casting defects that we see in actual castings.
Well, one of the things that's neat about simulation, and I would just say about 3D printing as
Uh huh.
well, is it gives you the ability to, what I would say, be more like an investment caster, because you don't have to worry about things like parting lines or parting planes and
Right.
things. And a simulation doesn't care. That is,
Sure.
if you can physically create the model, you can simulate what's going to go on that. So simulation, to my mind, facilitates the use of those sorts of things because it allows
Mhm.
you to very easily see what's going on. Uh, but I just selected this one. This is a big aluminum marine capstan. I wanted to show it because there's things like I've got a chill underneath here, and you can't see it until I go into wireframe view, but there's actually an insert in here. Well, it's a pad that ends up getting machined, but all those variations of things that you can do in the foundry, you can more or less do with simulation. And so to see, as you see, the effects of transitioning, to see what happens here, where you're going to go down, you're going to go through a filter, and that's going to cushion things or whatever. But it's interesting. Years ago, we were modeling a direct pour sleeve where you have the insulating riser sleeve, but at the base of it, there's a circular filter.
Mhm.
And so you pour directly into the sleeve, it fills the casting up, and then in theory, the filter flips out. Uh, we were able to show that if you didn't pour in the right place, you would see that you were getting extremely high metal velocities hitting the filter and basically flipping the filter out before it was done doing its job of filtering.
Mm. Sure. Yep.
And a lot of those things can be seen. So I wouldn't say I have a tremendous amount of experience working with Campbell's stuff.
Mhm.
Um, but
And
from
and
one
most
stand,
metal casters don't.
well, but I didn't talk a lot about it, but when we were looking at the fluid flow model before,
Mhm.
um, in fact, I might as well just go back to it. Uh, I mentioned velocity was one of the things we can look at. And Campbell's thing is, well, you don't want to go over half a meter per second
Right.
in any situation. Well, we can see right now that at the present, I've got 1.5 meters per second as an area there. It's not in the casting at all, but we can go through our process and we can say, I want to show cells outside the range, and I want to change. In fact, I can put in the number. Okay, so I can say anything that's going over 0.5 meter per second is going to show up in red. And I can do things the other way, and I could say don't show cells outside the range, and then I could have it set up that the only thing you'll see is parts of the casting or parts of the filling process where your metal velocity is exceeding that number. And we had talked a little bit before about the idea of bottom filling and getting this sort of splashing or fountain effect. Well, you can see that very clearly in those sorts of situations. Okay, where are we exceeding the metal velocity? And it's when it's getting pumped up through a bottom gate is most often where that occurs.
Sure. Yeah, if you're not controlling that with your sprue and the gates and the end gates, and having plenty of end gates, because typically bottom gating, I mean, you're going to want to have some sort of a non-pressurized so that your end gates are cross-sectional area. Your end gates are a minimum of 2 to 10 times the area of your sprue. So therefore, then you would never squirt it into there like a fountain. So definitely some rules in there to try to abide
Well,
by.
and we didn't, obviously, we're not doing a comprehensive thing of
Sure.
software functions, but when you go into gating design, you're looking at things like that. It's
Yes, sir.
first of all, it starts out, okay, what kind of material are you working with? And what section thicknesses are you dealing with, as well as your overall weight? It helps you determine an appropriate filling time. But
Yeah.
even if you select your own, once you establish that, it goes through the process of designing all the components, the sprue, the runner, and the gates, to meet that filling time. So if you say it's an aluminum casting, that's going to automatically skew you towards a slower filling because it's a more susceptible alloy, if you will, to the filling process. And then you would select a gating ratio, typically an expanding system like a 1:2:2 or 1:4:4 or 1:6:6, where the numbers are getting bigger, which means your metal velocities are getting slower.
Right.
Sure.
Oh.
Okay. Yeah, and I think that as we learn, and again, learning as much as we possibly can about removing and eliminating oxidation and the traditional thought process of AFS gating systems and things of that nature. I think that a tool like simulation and flow analysis are immensely helpful for the fact that it gives you a picture. Those heat maps and all that sort of thing for showing you the velocities and that sort of thing. Those are tools that foundry guys or the guy in the poor pattern shop that's doing rigging. He doesn't have that type of tool. So a foundry engineer that can actually help and use that as a quiver in the toolbox
Yeah.
to bridge that gap from engineering to actual shop floor guys and rigging, and to helping the guys on the floor understand what is this defect that we're seeing on the bottom side of this core. What is this? Well, just so happens I've seen case studies in our own facility of where you actually get oxidation from a turbulent fill, and it'll stick. It floats up and it sticks to the bottom of the core, and then they're in there going, "Well, what is this? What's going on here?" Well, when you simulate it, you can see it when you look at it, and you do that. And we use SOLIDCast here at KN Manufacturing as well. So I mean. Kind of preaching to the choir a bit, but it's good to see for me, because we use the older version of the software. It's good for me to see the version 9 as well, and certainly appreciate you coming on the podcast, David, and showing and letting people know kind of what's available and the services that you guys provide in house. If somebody doesn't have a foundry engineer, doesn't have the capital, or maybe cash flows tight and that sort of thing, that
Well,
they can
that's the
have projects.
problem today.
Oh, cash flow is never a problem in a foundry.
Yeah,
But yeah, no, it's outstanding. So, David, if you don't mind, and again, you share all your contacts and the places that you guys are available. If you're on LinkedIn or Facebook or website or YouTube or anything like that, and we can Perry can put those in the description of the podcast when we release them as well. But if there's anything else that you want anybody to know about, let the listeners know what that might be.
well, I'm old school. You know, I know what a telephone is or was. I used to dial them, and then I had to hang up because someone was on the party line. Uh, the best way to get a hold of us, frankly, is via email, and that's dave@finitesolutions.com. Uh, you can call me at 262-644-0785. But frankly, with this sort of stuff we're dealing with, most often we'll start with an email. Our website is https:// all that stuff, finite.solutions. And there's a lot of stuff available there. If
So
you
Dave, it looks like on the website you are worldwide. You've got people all over the world. Is that true?
Oh yeah, we have at least one system in well over 40 different countries. I haven't
Wow.
counted lately, but our primary user bases are, of course, all of North America. We have significant numbers in US, Canada, and Mexico. Brazil is a big place. Beyond the US, probably Australia is the next one. Jeff Merritt, who is our agent there, uh, he's just amazing. He To my mind, he is the most brilliant foundryman alive today, including John Campbell. Um, I have a lot of respect for Campbell as well, but Jeff started as a foundry apprentice in the 60s. He worked in the foundry for over a decade. He worked for Fasico for 15 years as a supplier, and he's spent over 30 years now as a foundry consultant and agent for our software. He's in his mid 70s, and he spends his days rigging castings using SOLIDCast.
Love it.
He's literally done thousands of them.
Wow.
And he is our go-to guy when we don't know how to use our software, because he's got the massive foundry experience. I've been working with foundries for over 40 years. I've never worked in a foundry. So
Okay.
from that standpoint, I'm good in that I can tell you where every function of the software is. Well, how do you do this? I can show you how to do that. But as far as, you talk about, okay, we're getting some sort of defect. What is that? Jeff will look at that. He can tell you what it is. He can tell you why. And he can also use the software to show you things like, for instance, hot tearing. Do we have a function that does hot tearing? Technically, no, we don't. But do we have tools that can indicate areas that are prone to hot tearing? And if you're changing the process, whether that's making them less prone, yes, we do. And that's all due to his efforts. He's just an amazing fellow. He tells
That's
pretty good
awesome.
stories too. He's a
Well,
lot like down
maybe
Dave.
we need to get Jeff
That's what I was just
on the
thinking.
podcast.
It would be absolutely phenomenal.
We'll have to
That's
reach out
awesome.
to him.
Okay,
Perfect.
that's
He
great.
literally is the most experienced foundry guy I know, and it
Okay.
such a range of things. I remember what was Sydney Olympics were 2000, I think, the year 2000. I was there in 1999, so I got to tour the Olympic Village and things like that prior to them being finished and used. And we went into the swimming venue, which didn't seem like much then. I mean, it had stands and stuff, but it was more, I'm thinking more like a high school pool, a little bit bigger. But he said, oh, well, that's because the back wall comes off, mate. And in 6
What?
months, they're going to remove the back wall and put in a 10,000 seat viewing area. And then when they're
Wow.
done, they're going to knock that off and put it back in. And you look up at all these connectors up in the ceiling. He goes, I did the methadone for that. And I said, so when we're watching the Olympics and the aquatic center collapses, we know who to blame. I did get a grin out of
Ah, that's so funny. Well, that is awesome. So, quick question before we kind of close her down. The SOLIDCast. If somebody doesn't have the expertise, they don't have an IT department, they don't have, a lot of horsepower with their computer, that sort of thing. Do you guys offer some sort of cloud service that actually has the horsepower and that sort of thing to run multi-cores and to really run things quickly? Or is it mainly you run it on your own PC at your own facility?
You run it on your own PC.
Okay.
It's not cloud-based. We're a tiny company. We don't have the resources to do something like that. But you know what? The stuff I was running there, this is
Hmm.
a 4-year-old desktop computer.
Okay.
I mean, it was a good one. It's an i9, but it cost under $2,000.
Okay.
So everything we do is multi-threaded and whatever thread and cord and whatever. Unlike other software companies which charge you by the number of cores or number of users,
Yes.
things like that, everything we
Very
do
annoying.
on it's a site
It's
license,
very annoying when they charge you like that.
and you can have it running simultaneously on every machine that you own. They're not connected up to things like that. We're not finding ways to peck at you. And like you say, you're using an older version of the software.
Yes.
There, I'm not certain of this, but there probably isn't another simulation vendor that will allow you to do that.
I understand. Yeah, and I cannot speak highly enough about SolidCast. We love the software; it works well, and we are going to upgrade this year. We will upgrade it to version 9.
Well, you'll be
So
doing it 5 times faster at least. So that
yeah,
on
well, and time is money.
is.
So looking
When I
forward to it.
started with this stuff and I was a poorly paid engineer, I didn't have the guts to tell anybody that they should spend extra money on a computer. And now I
Yeah,
say buy the fastest one you can get the day you get it. It's obsolete.
Yep.
right.
Forget about that because there's nothing you can do about it. But spending another couple $100 now, you'll save that by the end of the day tomorrow. So
Yep. Yeah.
literally,
So out of curiosity, just for my own edification, are there graphics cards or anything that you should stay away from that don't work real well with the software, or it doesn't
any
matter?
medium range thing will be fine. At present, we are not doing simulation processing with the graphics card, but that will be the
Okay.
next. That will be the next
So you are moving
phase.
towards GPU calculations then.
Yeah, well, I mean,
Everybody, yep.
Yeah.
however, what you saw was really zipping along pretty good.
It was. Yeah. So it's AI. I mean, is there anything that you guys are going to be using AI to help move the ball forward and try to take some of the guesswork out of it?
There's a lot of stuff actually with programming that we're using AI for now.
Okay.
I wouldn't say an AI function within the software yet, but
Okay.
A lot of developments happening through AI.
like I said, there's always more to
Yep.
do. There's always more
Sure.
to do.
All right. Well, David, thank you for taking the time to meet with us today. We really appreciate we know your time is valuable, and I think that the listeners will think that we'll really get a lot of benefit out of this. So expect to get some phone calls, I'm sure.
Love it. I'll have to plug
All
it back in after we had the ring earlier. I unplugged it during the break.
All right.
All
Thank
right,
you,
buddy.
sir.
Appreciate it.